Hi guys, so let's get started here. Okay, so we're just going to go back and look at the properties of water stuff. Okay, real briefly, we talked about two main categories for properties of water. The first one was the polarity. We said water is polar. That means that it has a positive end and a negative end. Hopefully you remember that. Because there's a positive and a negative end, that means that water is a charged molecule, partially charged. And we said likes dissolve likes. So water can dissolve anything that's charged, meaning other polar molecules that have a positive and a negative end, or ionic substances like salt, because ionic substances completely transfer electrons, so they are charged as well. But it can't dissolve things that are nonpolar, which would be like oil and other organic substances like dirt and wood, stuff like that. We said water exhibits hydrogen bonding. There's no such thing as a hydrogen bond. Hydrogen bonding is an intermolecular force. It only occurs if hydrogen is bonded to nitrogen, oxygen, or fluorine. Okay. And we use these dotted lines to indicate an intermolecular force. We probably have seen or remember hydrogen bonding in DNA back in biology. And then this is really important. We said that bonds are always stronger than any intermolecular force. So an ionic bond, a covalent bond, or a metallic bond will always be stronger than hydrogen bonding. Okay, but hydrogen bonding is the strongest of all the intermolecular forces. Okay, so keep those two things separate. Bonds over here, intermolecular forces over there. Then we just went through a list of all these different kinds of water properties. Cohesive, like co-captains, partners, so water sticks to itself. Adhesive forces, that means water sticks to other stuff. Why does it do that? Because of hydrogen bonding in both cases. And then we had some examples of that. The water sticking to itself was like droplets on the windshield that come together. Adhesive was like a coaster sticking to the bottom of a glass, or the formation of a meniscus in a graduated cylinder. That happens because of adhesive forces. Surface tension, we said it was like a network of water molecules all bonded to or all attracted to each other. And that happens because of hydrogen bonding. And then we had the Jesus Christ lizard, we have the paper clip, we have a bug on the water, all that good stuff. Belly flop in a swimming pool, I think that was another one we talked about. Capillary action, that's water's ability to be pulled up a constricted tube, a very, very narrow tube. It does that because of cohesive and adhesive forces, which it happens because of hydrogen bonding. An example we gave, I think, was doing blood, like getting blood out of your finger for diabetic patients and stuff like that, or having water going up the xylem in a root system of a plant. Boiling point. We said that water has a very high boiling point. Again, this is because of hydrogen bonding. Ooh, that should say bonding, not bonds. And that's because you have to put in a whole bunch of energy to overcome the very strong hydrogen bonding intermolecular forces. And the more energy you put in, the higher the temperature gets while you're adding energy. So water has a very high boiling point. And then we said it was a universal solvent. Now, this is the only one that doesn't happen because of hydrogen bonding. All right, this one is because it's polar. Okay, water is the universal solvent because it's polar. Okay, so like I said at the beginning of the lesson here, it can do that because, or it's the universal solvent because it can dissolve other like things, meaning all other polar substances and ionic substances because they're all charged. This is like the important part here. We said if you're going to be any point on the line, okay, if you're going to be any of these points on the line, then that means that you're saturated at that temperature and that amount of solute, okay? So I don't know if I can draw a line. Yes, I think I can, but I don't know how to do it. So I don't know. Anyways, let's say that we had, I'll have to leave them there. I don't like this. Okay, let's say that we had this temperature, or excuse me, this amount of substance. Maybe it looks like what, 137 or something like that. And let me just draw a line straight down here. Not entirely sure what temperature that's going to hit at, about 70. Okay, so we're at 137 grams and 70 degrees, and the substance that we're talking about is the substance that's on this line, which is the sodium nitrate. Okay, so if you are at about 70 degrees and you try and dissolve 137 grams of sodium nitrate in 100 grams of water, okay, then it will dissolve and it will form a saturated solution, okay? But if you try and dissolve, let's say, 140 grams of sodium nitrate, and notice I'm still talking about sodium nitrate. So if we try and dissolve 140 grams of sodium nitrate and we're still at 70 degrees Celsius, now you'll notice that this point that we're talking about here is above the line for sodium nitrate. Okay, we are now above the line for sodium nitrate, and that means that we are forming a super saturated solution. Okay, if we were to dissolve like 130 grams of sodium nitrate, I'm still talking about sodium nitrate here. If we were to dissolve 130 grams of sodium nitrate at 70 degrees Celsius, you'll notice that this point down here where the green lines intersect, that is below the sodium nitrate line. So we would have an unsaturated solution. That means we still could add more solute and get up to this saturated amount here. We talked about electrolytes and non-electrolytes. Okay, we said that electrolytes are a substance that can conduct electricity, and the reason that it can conduct electricity is because it can allow for the flow of electrons. The only way that it could do that is if it was a charged substance, meaning that it, that it is got ions dissolved in the solution. And the way that we get ions to dissolve in the solution is that it has to be soluble. Okay, so it's going to either be a strong acid, a strong base, or one of our soluble salts. And we know what those are based off of our solubility rules. If it was something that is not soluble, so it's a weak acid, a weak base, or not a soluble salt, then it was going to be a non-electrolyte. Some of those weak acids we actually said would be weak electrolytes. They would sort of they would make the light bulb light up dimly, but not like very brightly, and we'll refresh ourselves on that. So here we have an ionic substance that is going to be able to dissolve into its ions, which means that it can then conduct electricity. Okay, so soluble ionic compounds will fully dissociate, and that means that they're going to be strong electrolytes. Okay, then we had these three different light bulb situations. If it was a brightly lit light bulb, then that means that we had an ionic substance in there. So something like NaCl. Okay, I think that was our example. If it was a dimly lit light bulb, then we have a weak electrolyte, and in that case, it's going to be something that's polar, okay? So it has partial charges, not a complete transfer of electrons. So polar substances would be those weak acids that we just talked about, so organic acids like vinegar, which is acetic acid, or like alcohol. Okay, ethanol is another polar substance. Okay, and then if we had something that was not going to light up the light bulb, if it was not lit, then that's a non-electrolyte, and that would be some covalent substances that aren't polar. Okay, so a non-polar covalent substance like oil or sugar. Both of those would be good examples of non-electrolytes. Factors that affect the rate of dissolution. Remember, dissolution means breaking into its ions, okay? And that's different from dissolving, okay? Dissolving just means that it's being surrounded by the solvent, but dissolution means that the solvent is actually pulling it apart into its ions, okay? So if we want to speed up the dissolution of a substance, then we can crush it up, or we can heat it up, or we can stir it up. And so we talked about that and why each of those things do the things that they do. So crushing it up increases surface area. Stirring it up brings fresh solvent in closer to undissolved solute particles. And then heating it up adds kinetic energy, which increases motion, which increases contact between solvent and solute. And that is the main idea of all three of these things, is to increase contact between solute and solvent particles. Okay, talked about all of that. Molarity calculations. So we got our formula that molarity, symbolized by capital M, is moles of solute over liters of solution. And then we had some molarity calculation problems. So let's see here. What's the molarity of a solution made by dissolving 5.67 grams of potassium chloride in enough water to make 100 milliliters of solution? Okay, so we want to plug into our molarity formula. So we've got molarity is equal to moles of solute over liters of solution. This is not in liters, it's in milliliters, so we need to adjust that. We can do that quickly by moving the decimal place back 3 times. So, and this right here, that's not in moles. We need to turn that into grams, and we can do that by breaking it down. So we've got 5.67 grams of potassium chloride over 1, and then we need to get the molar mass of potassium chloride and put that down here on the bottom. That would give us 1 mole of potassium chloride up here on the top. So we'll figure out what that is. And then we would want to put 0.100 liters of solution down here on the bottom. And then that can give us our answer. So go ahead and get out your periodic table so that we can break it down. We need to know we've got 1 potassium and we've got 1 chlorine. Cool. Okay, so go ahead and do this dimensional analysis thing on top to get your moles. Then take that answer and divide it by 0.1 so that we can get our molarity. I'm getting 0.761 because we want 3 sig figs from the original problem. So 0.761 looks like the correct answer to me. So, we also, not sure if we talked about it or not, so I'm going to do it here very quickly. Our original equation right here is moles per liter. So we have moles sitting on top of liters. And then I'm going to put this molarity, this capital M, in this leftover triangle spot. If I were to give you the molarity of something and I were to give you the liters and I asked you how many moles was in that solution and you needed to rearrange to solve for moles, this is a simple 3 variable equation, and so I hope that you would be able to do the algebra to solve for that. But just very quickly, if you if you put it into this triangle over here and you set the triangle up so that it looks just like the original equation, this horizontal line right here is the division line, and this line, this vertical line right here, is the multiplication line, okay? And all you have to do is put your finger over the thing that you're looking for. So let's say that we were looking for moles, okay? If you cover up moles in that triangle, then what's left here is how you would set the equation up. Molarity times liters is equal to moles, okay? So you just cover up whatever whatever thing it is that you're looking for. So if I wanted to know how many liters there were, cover that up, and it shows me that moles divided by molarity gives me liters, okay? So that's just a quick, fast way to do something if you have like a simple 3-variable equation. It also works with a 4-variable equation, which we don't have yet. But you would set it up like this, where you'd have something in each one of these spots, and then the same rules would apply, okay? All right, so that's that. Dilution problems, this was another formula that you were told to memorize. So M1V1 equals M2V2. Remember that the ones are the beginning situation, and it's the more concentrated solution on the one side. And then on the 2 side, that's what you're going to end with, and it should be more dilute. Okay, so that means that molarity should be less for M2 than it is for M1, unless I think we had one problem on one of our worksheets where we allowed it to evaporate, and in evaporation, it's going to become more concentrated because you're removing water, you're removing solvent. Okay, so let's say that we have, I don't know, 9 molar solution of Bazinga. Yes, we have a 9 molar solution of hydrochloric acid, okay? And let's say that we have 40 milliliters of that, okay? And we want to make a 3 molar solution, okay, of the hydrochloric acid. Let's see how many milliliters of a 3 molar solution could we make? Okay, if I have this as my starting, requirements, I know that I want to make 3 molar solution. How much 3 molar solution could I possibly do? Okay, so in this case, we know this is M1 because it's more concentrated. We know this is V1 because that's how much I'm starting out with. I want to get it to 3 molar, so that's M2, and it's less concentrated than the 9 molar over here. And I'm trying to figure out then, of course, what is V2. All right, so I'm going to start with my original equation, and then I'm going to rearrange it to solve for V2. So V2 is going to be equal to M1 V1 over M2. And we just plug in. So looks like we're going to have 9 times 40 divided by 3. Okay. So y'all can go ahead and type that into your calculator. See, like 9 divided by 3 is 3. So it's just basically like multiplying 40 times 3. So 120. So we should get 120 milliliters is what we would be able to make. Okay. Now another question that I could ask is, okay, well, how much water would I need to add in order to do that? Because remember, if we're going to dilute something, we're adding solvent. Okay, so we have our original beaker here, and in that beaker we have our 40 milliliters of the concentrated acid. Okay, and we just figured out that we could make 120 milliliters, and that's this new line up here. That would be 120 milliliters. So the new question, the second part of this question is, how many milliliters of distilled water would we need to add to the original acid in order to get it diluted to the proper concentration? Okay, how many milliliters of water would we need to add in order to do that? Okay, George is telling me 80. Of course, that's a naked number, so I don't know if he's talking about 80 babies or bananas or oranges. Kaylin's telling me milliliters. Ian made the same mistake as George. Dreadful. Okay, Ian puts milliliters. Kenny got it. Maddox is telling me it's definitely 80 babies. All right. So yeah, we want to subtract 120 milliliters. We're going to subtract the 40 milliliters that was already there because that 120 is our total volume. And so that means that we had to add 80 milliliters of water in order to get to that total final volume. And that's it. Those are like the two types of question that I could ask you. I could ask you about any of the main four variables, M1, V1, M2, V2. So I could ask you anything about those four variables, and all you do is rearrange the equation. And then I could ask you how many milliliters of water would I need to add in and in order to do any of that, and you would just do a subtraction. So that's that for those kind of calculations. Okay. All right, I think that is everything then. So thank you for joining me today. Again, if you have any questions, please let me know, and I will be happy to answer them for you. Bye.